National Electrical Code Article 220.64 addresses the balancing of loads. This article is important because unbalanced loads on feeders can lead to several problems, including increased neutral current, voltage imbalances, and reduced system efficiency. Let's break down what this article entails and how it applies to practical electrical installations. The primary purpose of Article 220.64 is to ensure that loads are distributed as evenly as possible across the phases of a three-phase system. This minimizes the current flowing in the neutral conductor, reduces voltage drops, and improves the overall efficiency of the electrical system. An unbalanced load occurs when the current drawn by each phase of a three-phase system is not equal. This can happen for various reasons, such as unequal distribution of single-phase loads, different types of equipment connected to each phase, or variations in the operating conditions of connected devices. The effects of unbalanced loads can include, firstly, increased neutral current. In a balanced three-phase system, the neutral current should ideally be zero. However, when the loads are unbalanced, a neutral conductor carries the difference in current between the phases. This can overload the neutral conductor, leading to overheating and potential fire hazards. Secondly, voltage imbalances. Unbalanced loads can cause voltage drops that are not uniform across all phases. This can result in some equipment receiving lower voltage than others, affecting their performance and potentially damaging sensitive electronic devices. Thirdly, reduced system efficiency. Unbalanced loads increase losses in the electrical system. These losses are primarily due to increased current flow in the conductors, leading to higher I²R losses in the form of heat. Fourthly, transformer overheating. Unbalanced loads can cause transformers to overheat due to increased circulating currents and harmonic distortion. This can shorten the lifespan of the transformer and potentially lead to failure. NEC Article 220.64 provides specific requirements for balancing loads on feeders. The general rule is to distribute loads as evenly as practicable among the phases. This means that the electrical designer should make every effort to balance the load at the design stage and that the installer should follow the design intent during installation. The NEC recognizes that it is not always possible to achieve perfect balance, but it requires that the imbalance be minimized. Several methods can be used to balance loads on feeders. First is load assessment and planning. Before designing the electrical system, it is essential to assess the expected loads and plan their distribution across the phases. This involves identifying the types of equipment to be connected, their power requirements, and their operating characteristics. The second is phase rotation. One of the simplest ways to balance loads is to rotate the phases to which single-phase loads are connected. For example, if one phase has a significantly higher load than the other two, some of the loads can be moved to the lighter loaded phases. The third is dedicated circuits. For large single-phase loads, it may be necessary to provide dedicated circuits connected to different phases. This prevents one phase from being overloaded while others are underutilized. The fourth is load shedding. In some cases, it may be necessary to implement load shedding strategies to balance the load dynamically. This involves automatically disconnecting certain loads when the system becomes unbalanced. This is more common in large industrial or commercial facilities with sophisticated energy management systems. Fifth is using specialized equipment. Devices such as phase balancing transformers or static VAR compensators can be used to automatically balance loads on feeders. These devices are more expensive but can provide a higher level of load balancing in critical applications. The NEC does not provide a specific formula or percentage for load balancing, but it emphasizes the need to distribute loads as evenly as practicable. However, other industry standards and best practices provide guidelines for acceptable levels of imbalance. For example, a common rule of thumb is to maintain the load imbalance within 10 to 20%. This means that the current in any phase should not deviate more than 10 to 20% from the average current across all phases. To verify load balancing in an existing electrical system, several measurements can be taken. The first is current measurements. Use an ammeter or clamp-on meter to measure the current in each phase of the feeder. Compare the current readings to determine the level of imbalance. The second is voltage measurements. Measure the voltage between each phase and neutral. Significant voltage differences between phases can indicate an unbalanced load. The third is power quality analysis. Use a power quality analyzer to measure various parameters such as voltage, current, power factor, and harmonic distortion. This can provide a comprehensive assessment of the electrical system's performance and identify potential issues related to load balancing. If the measurements indicate that the load is significantly unbalanced, corrective action should be taken. These may include redistributing loads, adding dedicated circuits, or installing phase balancing equipment. The NEC also includes requirements for neutral conductors in three-phase systems. These requirements are closely related to load balancing because the size of the neutral conductor must be adequate to carry the maximum expected neutral current. According to NEC Article 220.61, the neutral conductor must be sized to carry the maximum unbalanced load. For household ranges and similar appliances, the neutral conductor can be sized at 70% of the phase conductors. However, for other types of loads, the neutral conductor must be sized to carry the full unbalanced load. In addition to load balancing, harmonic distortion can also contribute to neutral current. Harmonics are caused by nonlinear loads such as electronic devices, variable frequency drives, and LED lighting. These loads draw current in a non-sinusoidal waveform, which introduces harmonic currents into the electrical system. The third harmonic is particularly problematic because it adds directly in the neutral conductor in a three-phase system. To mitigate the effects of harmonics, several strategies can be used. Firstly, use harmonic filters. Harmonic filters are devices that are designed to reduce harmonic currents in the electrical system. These filters can be installed at the source of the harmonic currents or at the main service entrance. Secondly, specify harmonic mitigating equipment. When purchasing new equipment, specify devices that are designed to minimize harmonic distortion. For example, harmonic mitigating transformers and variable frequency drives can reduce the amount of harmonic current injected into the electrical system. Thirdly, oversize the neutral conductor. In systems with significant harmonic distortion, it may be necessary to oversize the neutral conductor to accommodate the additional harmonic current. The NEC provides guidelines for sizing neutral conductors in systems with nonlinear loads. Here are some examples to illustrate the application of NEC Article 220.64. Example 1 is a small office building. Consider a small office building with a three-phase 208-volt system. The building has several single-phase loads including lighting, computers, and HVAC equipment. To balance the loads, the lighting circuits are distributed evenly across the three phases. The computer circuits are also distributed across the phases, with heavier loads placed on different phases to offset each other. The HVAC equipment is connected to a dedicated three-phase circuit. After installation, current measurements are taken, and it is found that the current in each phase is within 10% of the average. This indicates that the load is reasonably balanced. Example 2 is a manufacturing plant. Consider a manufacturing plant with a three-phase, 480-volt system. The plant has a mix of single-phase and three-phase loads including motors, welders, and electronic equipment. To balance the loads, the large motors are connected to dedicated three-phase circuits. The welders are distributed across the phases to minimize imbalance. Harmonic filters are installed to reduce harmonic distortion from the electronic equipment. Regular power quality analysis is performed to monitor the load balance and harmonic levels. If the measurements indicate an imbalance or excessive harmonic distortion, corrective actions are taken. Example 3 is a retail store. Consider a retail store with a three-phase, 120/208-volt system. The store has various single-phase loads including lighting, cash registers, and display cases. To balance the loads, the lighting circuits are distributed evenly across the three phases. The cash registers and display cases are also distributed across the phases to balance the load. Energy-efficient lighting and equipment are used to minimize overall power consumption. Regular inspections are conducted to ensure that the load balance is maintained. Now let's address some common challenges and solutions in load balancing. One challenge is uneven load distribution. In many buildings, loads are not evenly distributed due to the physical layout or the nature of the equipment. Solutions include, firstly, redistributing circuits. Move circuits from heavily loaded phases to lightly loaded phases. Secondly, installing additional panels. Install additional distribution panels to better distribute the loads. Another challenge is harmonic distortion. Nonlinear loads can introduce significant harmonic distortion into the electrical system. Solutions include, firstly, harmonic filters. Install harmonic filters to reduce harmonic currents. Secondly, harmonic mitigating equipment. Use equipment that is designed to minimize harmonic distortion. Another challenge is changing loads. As new equipment is added or existing equipment is replaced, a load balance can change. Solutions include, firstly, regular monitoring. Conduct regular power quality analysis to monitor the load balance. Secondly, flexible design. Design the electrical system to be flexible enough to accommodate changing loads. Here are some best practices for implementing NEC Article 220.64. The first is detailed planning. Develop a detailed electrical plan that includes a load assessment and a strategy for balancing the loads. The second is accurate measurements. Use accurate measuring equipment to verify the load balance. The third is regular inspections. Conduct regular inspections to ensure that the load balance is maintained over time. The fourth is documentation. Document the load distribution and any corrective actions taken to maintain balance. The fifth is training. Train electrical personnel on the importance of load balancing and the methods for achieving it. In summary, NEC Article 220.64 is a crucial requirement for ensuring efficient and safe operation of electrical systems. By balancing loads on feeders, you can reduce neutral current, minimize voltage imbalances, improve system efficiency, and prevent transformer overheating. Careful planning, accurate measurements, and regular inspections are essential for implementing this code requirement effectively. By following the guidelines and best practices outlined in this discussion, you can ensure that your electrical system is properly balanced and operating at its optimal performance.